This is the first robot I ever built. It's called Hexapod because it has 6 legs which allow it to walk in tough terrain. This robot took me a whole year to build, which is why it's one of the best hexapods in the world. Or maybe not, but it can do some cool stuff anyway. I'm gonna show you the journey of this robot from day one. The mechanical engineering and electronics. You'll see the highlights, and there were even a few mistakes along the way. For a deep dive, I made a long version on my second channel where I explain everything in detail. But here, I'm just showing the fun stuff. Now, let's build a hexapod robot. At day 1 of the actual build, I had an optimistic view.
In the next 2 months, I'm going to build a hexapod robot that's going to climb walls like a spider.
This estimate turned out to be inaccurate. I started by designing a single leg. It's gonna use 3 of these servo motors. This is the minimal amount because you need at least 1 motor per each axis it's gonna move along. I opened up Autodesk Inventor, which is a CAD software for 3D modeling. After finishing my shitty model of the leg, I exported it as an STL file and opened it in Cura. I set the infill to 20%, saved the G-code and started printing. For the material I chose PETG because it's stronger than PLA, or at least so I've heard. I glued all the pieces together and coded a basic movement. I coded the movement in angles, so the leg doesn't move straight. And I also fucked up the CAD, so one of the axes is crooked. But that doesn't really matter because it was just a prototype. At day 5, I focused on the inverse kinematics, and I'll let past me explain what that is.
I built this one leg, which is made from 3 servo motors. I can set the angle of each motor and the leg will move to some position. This isn't very useful since the movement is essentially random. What I want is to tell the leg to move to some position and let the robot figure out the angles. This is called inverse kinematics. I solved it by writing down the equations and transferring them into code. I can now move the leg in the X, Y, Z or any other direction I want.
I have IK as a function in my code, which translates the X, Y and Z into theta 1, 2 and 3, so I can code the movement of the leg in spatial coordinates and the code translates it to the joint angles. Since I could easily code the movement of the leg, it was time to make the leg path.
So far I've built one leg which can move in the X, Y and Z axis. My aim is to combine these movements in a specific way which allows the robots to walk. I could let the leg trace out a triangle like this. The problem are these sharp corners. The leg is moving in one direction and I'm telling it to move the other way the next millisecond. This causes the motors to overload. Instead of a triangle, I am using this smooth path which is called a Bezier curve. This curve is C2 continuous, which roughly means that the force acting on the leg changes gradually and not abruptly. This makes the leg movement smooth and doesn't wear out the motors.
In just a week, I had made a full working prototype of the robot's leg. So at day 12, it was time to design the rest of the robot. By this time, I had already ordered another 16 servo motors. All the parts I used for this robot are gonna be linked in the description. You can also check out my sponsor, PCBWay. The modeling took me 5 days, which sounds like a lot, but this assembly has 150 parts and they all have to fit together. This is the body of the robot where the electronics goes. I wanted to make the robot as small as possible, but it ended up being over 70 centimeters wide and now it barely fits through the door. 34 days later, I was still waiting for the motors. You see, AliExpress ships the order to your country, this is fine, but from there it gets delivered to your home by a local delivery company. Which means I'm fucked, because in my country, the delivery company is this piece of shit. So I was just praying it would get delivered sometime, because I spent $200 on the motors. While I was waiting, I printed the body and a single leg. I chose ABS because the PETG I tried before wasn't rigid at all, and ABS should be even stronger. I joined the parts together with bolts and square nuts because I didn't know that heated inserts exist. I was happy with how it looked, but it was really heavy. I redesigned the tibia, which is this part, to add a greater range of motion. I attached the leg to the front of the robot, so I had to rotate the leg path by 60 degrees. I did this by adding 60 degrees to the first joint, which wasn't ideal since it rotated the path around that joint instead of the center of the leg path. I was starting to lose all hope, but at day 62, 2 months after I had placed the order, the motors finally came.
I replaced the old ones, printed some new parts and assembled 2 more legs. I updated the code so it generates 2 more paths for the added legs. I tried powering it with the notebook, but the motors draw too much current, so I had to switch to LiPo battery already. The 11-volt battery is connected to a buck converter, which reduces the voltage to 7 volts, which the motors need. I also added a switch for the battery. Next, I will properly write a code for turning the robot while printing the remaining 3 legs.
Yeah, this was a scam. Since the robot had 3 legs, I had to upgrade the power supply. Before I was using a notebook to power the Arduino, to power the breadboard, to power the servo motors. But the Arduino 5-volt pin doesn't have enough current to support 9 servo motors, so I switched to a LiPo battery. Day 95 was a pivotal moment. It was the first time I made the robot walk. I was at the hospital for the last month, but I managed to assemble the remaining 3 legs. I wrote a code to make them move and tested it. Then I printed a stand for the robot, so I can test all of the legs easily. Since I finished all the legs, I let the robot take its first steps. The robot only walks forward. It has no control system or sense of the environment yet. It walks slowly and takes small steps, because I miscalculated the power requirement. I already ordered a battery with lower voltage, so I don't have to use the buck converter, which only provides 15 amps. The battery has plenty of power, but the buck converter has a maximum current of only 15 amps, which is barely enough for the robot to walk. The motors would also start moving randomly, or they wouldn't move all at the same time. At day 112, I improved the electronics. The old robot didn't have enough power, because I was using a high voltage battery with a buck converter which didn't provide enough current, so I had to redesign the circuit. I bought a 7-volt battery and connected it directly to the motors, so I don't need to worry about not having enough current. Next, I changed the breadboard for an Arduino shield, which lets me connect all of the motors easily. I also soldered a flyback diode and a capacitor on the Arduino for more stable power supply. Now the robot can walk faster and take bigger steps. In the next video I will write a code to make the robot run and maybe add a remote control joystick. The sensor shield I added has the power, ground and digital pin next to each other, which makes it easy to connect the servos. Now there's still one thing I haven't talked about yet. Pretty much from day 1 I was working on a remote controller behind the scenes. I bought NRF24 chips and a HC05 in case the NRF didn't work. I assumed this was gonna be pain, but I wasn't prepared for what was to come. After weeks of work, I managed to make a transmitter with an Arduino Uno, 2 NRF chips and a joystick. Choď tu flašku. Pořádně. Plnou parou vpřed, dělej. To se nezničí, ne? Up to this point, the progress was fast. It might have taken me 100 days to get here, but I spent most of the time waiting for the motors to arrive and being in a hospital. But from this point on, it all started going downhill, and I wouldn't upload for the next 250 days. The wireless communication was abysmal. It almost never worked and I had no idea how to fix it. I tried some tips from the internet, but none of them helped. Then the sensor shield blew up. I realized it was supposed to be powered by 5 volts, so it was completely useless in my case. I looked for a shield that could power 18 servomotors, but couldn't find one. On top of that, the robot started falling apart, because the 3D printed parts from ABS weren't strong at all. This meant I had to reprint the entire robot. Those were major issues, and since I wasn't even sure if I could fix them, I considered not finishing the robot. But I decided to keep going. I went full sunken cost fallacy and spent a bunch of time working on the robot. I decided to make my own shield with a custom PCB, but since Acer has already made one for his Hexapod, I just ordered his PCB and soldered it. I started reprinting all the parts with PLA and upgraded the robot's code in the meantime. I added foam to the robot's feet to prevent them from slipping. I got fucked over by the delivery company even harder than before. I started using heatset inserts for the bolted joints. And I redesigned the robot's body. I spent most of the time trying to fix the wireless communication, but I was out of luck. With the newly printed parts, I was able to ramp up the speed and get a decent performance. I like this step he makes at the end. I got to a point where the robot was kind of working, apart from the remote controller. So I did some more coding and created a video showcasing the upgrades. Since I finally had something to show, this marked the end of my 200-day pause and I started recording the progress on YouTube again. I even managed to get the remote control working, but ever since I made the robot stiffer, the legs started vibrating. So this was the focus of my new video at day 377. This is my robot I've been working on for the past year. When it walks, the legs just start vibrating like crazy and he looks like he's about to give a presentation. To reduce vibrations, I added friction caps to the main joints. Unfortunately, they weren't strong enough. The square shaft kept breaking, so I made it bigger. This meant I had to redesign other parts as well. And because of my shitty design of the robot, changing the parts was pure pain. I have to disassemble the whole leg just to change these 3 parts. And eventually I'm gonna have to do this for all of the legs, so it's gonna be super painful. Testing the new friction cap went well, but a different issue emerged. These feet are terrible. They dig into the ground and also slip. I originally had a piece of foam at the end, but it wasn't strong enough. I decided I was gonna make new feet from silicone, so I printed this 2-part mold. The silicone is made by combining 2 parts, A and B, and I just realized that my part B is hardened, which it shouldn't be, so I'm just gonna dilute it in some alcohol and see if it works. So, as I said, I'm just gonna crush the part B into powder. It looks like it's getting solid, so I'm gonna pour it into the mold and hope for the best. Unfortunately, it did not solidify, so I ordered new silicone. With the vibrations sorted, I wanted to make a remote controller, so I made a prototype at day 393. I've been making some serious progress on my robot, although I haven't upgraded the remote controller yet. This is mainly because it's perfect, but I'm gonna make some minor adjustments nonetheless. And with them, the robot should be able to do some interesting stuff. I started by making a sketch and choosing which controls I was gonna use. Then I made a CAD model of the controller, printed it and started assembling the parts. Both of the joysticks are bolted to the base plate, the two sliders click into place, the button is bolted, the switch and the battery click into place, and there's a breadboard in the middle. Alright, the easy part is done, now I'm gonna wire up the electronics. I connected the battery through a switch to the Arduino. I added a button for changing the robot's gait. I wired up two sliders and two joysticks to control the robot's movement. And I added a 443 MHz transmitter. If this isn't the best looking controller you've ever seen, I don't know what is. After a few painful hours, I managed to connect the robot to the transmitter. You control the movement of the robot with the right joystick, and with the right slider you control the height of the robot. If you move the left slider, you control the radial distance of the legs. And now I'm gonna change the gait, and you can see he walks differently. He lifts the legs one by one. And now I've changed it back. The silicone I ordered last video came, so I could finally finish the feat. Let's see how he walks with his new feet. Fuck. At least my dog likes them. I applied super glue to the feet and they ended up working well. At day 444, I added the most exciting update yet. Today I'm gonna take all my engineering knowledge and teach him how to high five. Have you ever wondered how this robot walks? Each leg moves in a straight line, so the robot goes forward, and then it lifts up and returns to the starting position. I had previously generated the leg path by manually coding it, but now I was gonna do more advanced movements. I decided to animate the robot in Blender, so I didn't have to manually code each leg. To recreate my robot in Blender, I started with a leg. I first modeled the three links. I created armature to define the linkage. I added inverse kinematics to make the leg move. Finally, I modeled a body, copied and pasted the leg 5 times. Then I was able to animate the robot. You can keyframe the location, go a few frames in the future, move the robot somewhere, keyframe it again, and then when you play it back, the robot moves. I've made this animation, and then I wrote a script that saves the positions of the legs. It generates this text file with all of the positions. Then I just take this and paste it into my main Arduino code, load it to the robot, and it does exactly what the animation does. So instead of generating curves for each of the leg, I just do this animation and then I paste it into the main script. I had planned to make the robot dance, but there was a difference between the simulation and real life. So I opted for a simpler animation. But there was still one thing I had to take care of first. I control the animations of the robot with this controller, and don't be fooled by the beautiful design, it's actually pretty shit. It only has one button and I need at least 3, so I'm gonna upgrade the controller and then I'm gonna make him high five. In case my voice didn't give it away, I'm super excited. Actually, because even though my channel is small, I've already secured my first sponsor, and it's PCBWay. Do you see this mess? PCBs let you transform all the ugly wiring into a nice little circuit board. And designing them isn't even that hard. I've designed my very first PCB in 2 days. And if your PCB is small, it costs only $5. So if you want to upgrade your project with PCBs, go to PCBWay and you'll get a $5 discount for your first order. These helping hands are great. Man, I hate soldering, but this is cool. Dope. Nice. Alright, let's make some animations. For the high five, he just lifts up his leg, waits for the hand, and then executes the high five. To make the robot dig, he's gonna sit back like this, then he's gonna dig into the ground with his 2 front feet. Alright, let's have some fun. It's been a long journey, but we have finally reached the end. These are the most recent clips I filmed when I took the robot shopping at day 440. This was my first time using an Arduino, 3D printing and generally building a robot. It took over a year to build and apart from some exceptions, I really enjoyed it. I planned to do so much more with the robot, but after some consideration, I decided it was time to retire it. I'll explain why I retired the robot in my next video. Now let's zoom out. Look at the biggest challenges and what I would do differently. Wireless communication. This was the biggest bottleneck of this project. I spent so much time on it that it hurts to talk about. The best I got was an RC that occasionally worked within a 2-meter range. I tried many things but never got it to work. I'll try using ESP now for my future robot since I've heard it's not completely shit. Weight. The robot weighed 5 kilograms, which is 2 kilograms more than I had planned. ABS. I had printed the robot in ABS, which prints terribly on Android 3. This paired with the high weight resulted in mechanical failures of almost all the parts. Sensor shield. I hadn't checked the wiring diagram, which would have told me it wasn't usable in my situation. Non-iterative design. I hadn't tested the robot properly and built the first design I had in mind. I then had to reprint the entire robot. Modularity. I had designed the robot to have as few parts as possible. Then, when I needed to change one part, I had to take apart the whole robot. Hexapod's PCB. There was a short circuit somewhere in the Hexapod's PCB, so I couldn't upload the code when the PCB was connected to the Arduino. This made it a nightmare to code the robot. Vibrations. The servos vibrated a lot, which caused the bolt to unscrew. Compliance. The robot had no compliance, so when the robot's leg caught something, the servo broke. Upper body. I had put the cable holes in the upper body, so when I wanted to open the robot, I had to take up all the cables first. Now I'm gonna talk about what I've learned and some tips I would have used. When prototyping, design everything as simple as possible. You can improve the aesthetics and optimize once you have a working prototype. Make the design modular so you don't have to disassemble the whole robot to change a single part. Make the design expandable. For example, add mounting holes for attaching things in the future. Make it easy to access the main parts like motors and the electronics. Add a hole for the Arduino cables so you can code the robot without disassembling it. Don't print in ABS if you don't have a printer for it. Use thread locker to prevent bolts from getting unscrewed. Make a voltage reader for your battery first, so you won't destroy it by draining it. Make custom PCBs. You'll save yourself time and have the electronics more ordered. Don't buy the cheapest solder. You'll save time and energy. Also use flux and helping hands. Make the code easy to read. Use commands a lot. Use functions, don't repeat code. Give variables and functions meaningful names and explain them in comments. Document the code. Write roughly what the code does at its beginning or in a text file. I've learned a lot and will definitely make a video in the future to finish what I wasn't able to this time. But now I want to make a different robot and work on my other projects. The Hexapod ended up costing about $300 to $400. All the parts are in the description. Thank you for watching and I'll see you in the next one.